Good day. Our topic for today is hypergeometric distribution. Hypergeometric distribution is often used in sampling without replacement in a small population or destructive sampling. For example, if we have an illustration here which indicates as our M, which is our limited size evaluation, and M in every trial has only two outcomes, which is success, success, and also have M minus K, which is our failure. So let's say if we have to take some sample with this population, and let's say this illustration is our sample population, and this sample population in every trial has only two outcomes in every trial. So we have two outcomes also, which is our N success and N minus X, which is our failure. What is the probability that the sample of size n has x successes? P is equal to number of ways to satisfy a constraint divided by the total possibilities. Number of ways that satisfy a constraint in a population is a certain number of success and a certain number of failure, which is the outcome of the two is equal to number of ways that satisfy a constraint. If you remember, successes in a small population is denoted as x, and failure in a small population is denoted as n minus x, as well as k successes in a limited population, and m minus k is a failure in our limited population. The success and failure, then the product of the two is equal to number of ways that satisfy a constraint. And also we have P is equal to K choose X times M minus K choose N minus X divided by M choose N, which is our total number of possibilities. Now let's find the mean and variance of hypergeometric distribution given by this formula for x is equal to 0 up to n. In deriving the formula of hypergeometric distribution, we need to apply this identity. So these three identities might helpful to solve the mean and variance of hypergeometric distribution. So we have the expectation of x, summation of x, f sub x of f of x. And now we have, by substituting the given, so we have summation of x times the quantity of k taken x multiplied to quantity of m minus k taken n minus x divided by the quantity of m taken n, which is our x ranges from 0 up to n. And also we have summation of x times the quantity of k taken x multiplied to m minus k taken n minus x divided by the quantity of m taken n, which is our x is ranges x is equal to 1 up to n. So we have this part will become 0 since our x is 0 when it's substituted to x. The whole equation becomes 0, so we have 0 plus summation of x multiplied to quantity of k taken x multiplied to quantity of m minus k taken n minus x divided by the quantity of m minus n, ranges from x is ranges from 1 to up to n. So by applying the identities, we can get this and as well as this denominator. So we have summation of n times k over m multiplied to the quantity of k minus 1 taken x minus 1 multiplied to the quantity of m minus k taken n minus x divided by the quantity of m minus 1 taken n minus 1. Since n and k over m is a constant, we need to put it in outside of the summation. So we have the summation of the quantity of k minus 1 taken x minus 1 multiplied to quantity of m minus k taken n minus x divided by the quantity of m minus 1 the quantity of n minus n. So the first observe, we're going to change the variable in order for us to know if we can still manipulate the hypergeometric distribution. Now we have the n times k over m summation of quantity of k minus 1 x minus 1 multiplied to quantity of m minus 1 minus k minus 1 taken n minus 1 minus x minus 1 divided by the quantity of m minus 1 taken n minus 1 is equal to n times k over m summation of k prime taken x prime multiplied to m prime minus k prime taken n prime minus x prime divided by the quantity of m prime taken n prime. So this part, what we have done here is we change the variable so in order for us to know if we can still manipulate the hypergeometric distribution formula with different parameters. And now we have n now we have summation of n. Now we have the mean of hypergeometric distribution, which is n times k over m. So because this part is equal to 1 by our identities, according to our identities.